All right, let's dive right in. Today, we're cracking the code on what is probably one of the most predictable questions on your entire chemistry exam. Think of this as your special insider's guide, a strategic deep dive to help you absolutely nail question 5. I mean, just imagine that for a second. What if you could walk into that exam hall already knowing the structure, the key ideas, and even the most likely topics you're about to face? What if you could swap all that guesswork for a solid, calculated strategy? Well, guess what? For question 5, you totally can. So here's what we've done. We've gone back through years of exam papers. We've spotted all the recurring patterns, and we've put together a blueprint. This isn't about just, memorizing the whole textbook. It's about smart, targeted prep based on what the data tells us. So here's our game plan for today. First, we're going to crack the question's code. Then we'll get into the 2 core concepts it's always built on. After that, we'll hit the most frequently asked topics, make some pretty bold predictions for 2026, and then wrap it all up into your final strategy. Okay, let's get started by decoding this thing. Seriously, stop thinking of question 5 as just some random problem. It's more like a puzzle. It has these specific pieces that get used again and again. And once you know what those pieces look like, putting the whole picture together gets a whole lot easier. All right, let's get to the foundation. You see, every single version of question 5, no matter what year we're talking about, is built on 2, well, let's call them unshakable pillars of chemistry. If you can master these 2 chapters, you've honestly won half the battle already. And here they are! On one side, you've got the mole concept and stoichiometry. This is all about the math, right? The numbers, the calculations, the quantities and reactions. And on the other side, you've got electrolysis, which is all about the practical stuff, seeing how electricity can actually create chemical changes. Every question 5 is basically a mix of these 2. Okay, now for the really useful part. Since the question always pulls from the same 2 chapters, it also tends to repeat the same types of problems. You can think of these as the greatest hits of question 5. These are the topics that just keep showing up year after year. So let's look at these high-value targets. First up, Gay-Lussac's law. This almost always comes up as a numerical problem about gas volumes. And listen, here's a pro tip. The number 1 mistake people make is forgetting to balance the chemical equation first. Always, always double-check that. Then there's percentage composition, another classic calculation. On the electrolysis side, you have to know 2 things: the specific reactions for acidified water and the basic rules of electroplating. You master these 4, you're in a fantastic spot. Let's do a quick-fire round of some definitions that just keep coming back. First on the list, vapor density. This one is everywhere. The key phrase to remember here is that it's a ratio. It's the mass of some gas compared to the mass of an equal volume of hydrogen. And, this is crucial, it's all measured under the same conditions. Don't forget that last part. And this is why that definition matters so much. This simple little formula is the bridge that connects vapor density to molecular mass. Because vapor density is compared to hydrogen gas, which has a molecular mass of 2, you just have to multiply it by 2 to find the mass of whatever gas you're working with. You are absolutely going to need this, so burn it into your memory. Okay, here's another classic that really tests if you understand a practical process. Just think about it for a second. In that huge industrial process for extracting aluminum, why do those big carbon anodes have to be swapped out all the time? What's going on there? And there's your answer. It's all about an unwanted side reaction. The oxygen that gets produced at the positive anode is super reactive, especially at those crazy high temperatures. So it literally just attacks the carbon anode, oxidizing it and carrying it away as carbon dioxide gas. The anode basically gets eaten away. Okay, so we've looked at the past, we know the patterns. Now, let's do something even more fun. Let's look to the future. Based on what we've seen and the topics that are kind of due for an appearance, we can make a really solid forecast for the 2026 exam. This is where you get your strategic edge. First things first, our analysis strongly suggests that the main calculation problem this time is going to be a big one. We're predicting a full 5-mark question. That means there is absolutely no room for error in your calculations. This one question could be a huge part of your final score. So, what are our big predictions? For that 5-mark numerical problem, we're betting on a calculation of empirical and molecular formula from percentage data. For the process-based question, get ready for the electrorefining of copper. And for the theory part, the focus is almost certainly going to be on Avogadro's law. So let's break down that copper experiment, because you have to know the setup. The negative cathode is where the pure stuff collects, so you start with a thin, pure strip of copper.
The positive anode is the big, impure block you're trying to clean up. And the whole setup sits in an electrolyte like copper sulfate solution, which lets all the ions move around.
Now for our theory prediction. Avogadro's law. This is such a core concept. The easiest way to think about it is like this. At the same temperature and pressure, all gas molecules like to have the same amount of personal space. So it doesn't matter if they're huge molecules or tiny ones, if you have equal volumes of any gas, you will always have the exact same number of molecules inside. And that law leads us to one of the most useful numbers in all of chemistry. You ready for it? 1 mole of any gas, I don't care if it's oxygen, helium, whatever, will always take up 22.4 cubic decimeters of space at standard temperature and pressure. This idea, molar volume, is the secret key to solving tons of gas calculations. Okay, we have cracked the code, we've gone over the classics, and we have looked into the future. Let's pull all of this together into one clear final strategy that you can start using, like right now. Here it is, your blueprint. Step 1, build a rock-solid foundation in those 2 pillars, mole concept and electrolysis. Step 2, memorize the key definitions and formulas we talked about until you can say them in your sleep. Step 3, focus your practice time on our predictions. So that's empirical formula problems and the electro-refining of copper. And finally, number 4, always try to understand the why behind a process, not just memorizing the steps. So, there you have it. You have the blueprint, the strategic guide to absolutely crushing question 5. The patterns are all laid out for you. The only real question left is, where are you going to start? Are you going to jump into the math of the mole concept first, or get hands-on with the practical side of electrolysis? The choice is yours.